Hello everyone and welcome to my video explaining how the Memorymoog power supply works. You might think it's just a normal supply. Besides the rumors that it gets hot, which I don't think is the supply's fault, to be quite honest. I just think that's a side effect of the power supply design at the time, and it's more to do with the voltage coming out of the transformer, which is quite high, higher than what we would use when we were designing today. When you're dropping a lot of voltage, you have to get rid of a lot of heat. So it's not really the supply itself's fault. It's more of a whole system-wide thing to do with the transformer, but I'll go into that a little bit later. The purpose of this video is to explain how the actual power supply board works, because this is very different to a normal supply. It is sort of similar to how the early CS series supplies worked. So the Yamaha CS50, CS60 and CS80, they had sense lines on the main voltage rails. So the 5, although I think in that other synth it's different. I think there's an 11 volt and -5, all that kind of stuff. This one's more basic, just +5, +15, -15. Sense lines on all three, which don't go anywhere useful. They actually just go to the connect. They go to the end of the wires on the board. I'll explain that later. But there's also sense lines on the grounds. So each of the three supplies here, the 5, 15, -15, they're completely isolated from each other. The grounds are completely isolated from each other. All the rails have sense lines, all the grounds have sense lines. So when you unplug this power supply, it stops working. Well, at least the 5 volt side of it stops working. The other two are no longer referenced to each other, and they give out the wrong voltages because of the way there's some bypassing working, which I'll explain later on. But to get the right voltages from this supply, you must have it plugged in. Now, I've seen a lot of people speculate on the internet about, oh, I always calibrate this supply with it plugged in, so under load it's the right voltage. That's sort of what happens, but for the wrong reason. It's nothing to do with the loads. It's the way the supply internally bypasses. When you unplug the plug, you get a different set of voltages, and I can explain that and what to expect. And I can also tell you how to set up your own connections on this plug so that you can calibrate it accurately without having to plug it in. But all of that will become clear once I explain how it works. I will screen share with you on the schematics and we will explain all of that. But first, let's start with an experiment, because of course now is the time to experiment, because I mean most of the synth isn't there. It's actually over there. So it is less likely that I'm going to blow stuff up, which is great. And also, this is really interesting, and part of the whole reason for the video is to show you what happens when you do unplug and how to deal with it. So let's turn it on and we will have a look at some voltages. Okay, so we are on, and my probes, the red one is on the 5 volts, the blue one is on the 5 volt raw. It's labeled in the schematic as raw. It's actually just the same voltage that's used to generate the 5 volts, but before it's gone through the regulator, so it's just after the bridge rectifier being filtered by the main big capacitor. The ground I'm using for this, it's the same ground at the moment because this connector is good. So one of my probes is just on the main ground wire for this DMUX power supply distribution board, and the other one's on the top of that big capacitor. Same ground at the moment. And voltages that we are getting are 5 volts, which is great on our 5 volt main output. And on the raw, we've got 11.75. Interesting to note, on the raw, there is a bit of ripple, and that's because it's after the filter cap, after the rectifier. So it's a full wave rectifier, so this should be about 100 hertz because of 50 hertz Australian mains voltage. So the bottom of the wave has been flipped up and then smoothed by a capacitor, so the peaks here on the ripple should be roughly about 100 hertz. we get about 60, it's usually about 68 millivolts, somewhere between 67 and 69. So 68 millivolts ripple, which is not bad. It's good to, when you're measuring voltages, if possible, to also look at them on a scope, because it allows you to see any noise or ripple. Now you can see the 5 volts here, there's no noise. And this is pretty much as good as you're going to get for a 5 volt supply of this type. So we know we're good with the 5 volts. We know we're good with the raw. Now that raw 5 volts, which is actually 11, that's used, that goes to the display on the front. So let's unplug it and see what we get on our 5 volts. Okay, so now I'm measuring from the same pins. I'm measuring my 5 volts and I'm measuring the 5 volt raw signal, but this time I've unplugged the power supply cable and I'm just measuring it from the board itself, and have a look at what we get. 5 volts is now pretty much 0, and we get about 12 for the raw. Now the 12, that's still expected, it's not under load now, it's not really going anywhere. To be around 12 is still okay. Our rectifier is still working and it's still being smoothed, but of course we're getting 0 for the ripple because there's really no output, there's nothing pulling those peaks down. So we've really just filled the cap up full and there's no current coming through the rectifier anymore. So it's not exactly what you'd expect, but it shows that it's working. We've filled that line up to 12. It's got nowhere to go, but it's working. 5 volts though, nothing. Now what's happened? Did we blow up our supply? Well, no, we didn't. One of the quirky things about this supply board, which I'll show you on the schematics again, is that when you unplug the plug, the 5 volt side switches off, and the reason is it's powered by the 15. Now the 15 is still on. The only two rails that are still on are the 15 and the minus 15, but the problem is when you unplug the plug, the circuit loop through the 5 volt regulator from the 15 and then back again is broken. So there's no current flowing through that regulator anymore, so it switches off. 15 volts one way doesn't power anything. You need to have current flowing. So it doesn't work when you unplug it. Now, if you think that's interesting, watch what happens when I do the same experiment to the 15. I won't do the minus 15 because they're basically the same concept. I'll show you on the... Well, they're exactly the same supply, believe it or not. I'll show you on the schematic. Oh, that's another story. But basically, in a nutshell, the 15 and minus 15 in this supply is the equivalent to one of those schoolboy supplies when you add two 9 volt batteries together and you join the positive and negative terminals into a common, and then you get a plus minus 9 volt supply. That very basic concept is exactly the same way this works. There's two identical 15 volt positive supplies that are just joined, one common to the ground and one common to the plus 15. So you end up getting plus minus 15 with the middle joined. It's just odd. I'll explain in the schematic, but first let's do the experiment again with the 15 and we'll see what happens to the voltage. Okay, so I'm plugged in again and looking at the 15 volt supply this time. Now what I forgot to tell you in the last experiment is that I stopped using the ground on this board, obviously, because the plug was unplugged, and I used all my grounds were on the common 5 volt supply ground, which is the top of this big capacitor. So in this one I've had to change my ground again because when we pull the plug all the grounds are isolated, so I'm using the 15 volt ground as labelled on the schematic, but I could also use the ground on this board at the moment because we're plugged back in. So the 15 volts is on. We're getting 15.09. Absolutely no noise. This is a really great supply when it's serviced well. Now let's unplug the plug and see what we get. Okay, so we're plugged, we've unplugged and the probes are back on. This is exciting. What are we going to get? It's 16.5, nearly. 16.5 volts. So it's gone up significantly. Now in this case, the 15 volt supply is still on. The sense line is actually still connected, but it comes back via a diode, so the voltage that comes back is lower than the supply is expecting. So it tries to compensate, and we kind of get in this loop, and so it goes way over 15. So it's just more than the 0.7 volts of the diode, because we get this feedback loop. So if you calibrate on this, you'll be significantly lower than 15 when you eventually plug the plug back in. Now I can show you how to get around all this and calibrate with just like this, unplugged, by making a few connections. But first we'll have a look at the schematics, we'll explain what we've just seen, and have a look at how it works. Okay, so here is the schematic for the Memorymoog power supply. The three rails that you would normally expect, +5, +15, -15. Now the way they're regulated are by 723 ICs, and this wasn't common at the time. This was early to mid 1980s, so 81, 83, and the linear voltage regulators that were all in one piece that you didn't need external transistors for were much more common at the time, and the current that we're dealing with here is not uncommon for those to handle, particularly the LM317337. Their typical is 2.2 amps, but here we've only got one, so I mean they could have been used. They would have been expensive at the time though. The normal like 7805, the 7815 and 7915, they would be a little bit more near this limit. I think their typical was around 1.5 amps, but most of the time you would design for a 1 amp output, and this is slightly above that. So that may have factored in the decision to use 723, but those linear regulators also have a provision, and it's probably even easier to use external transistors with those than it is with the 723. There's still a lot of components you need for a 723. So I suspect that this is just cost, but they do the job the same. At the end of the day, there really isn't much difference, besides there's a few more components here and they're a little bit harder to probably set up. But I mean, it works. That's not the problem with this supply. The problem is in the way, or in the number of sensing lines that are used. You would normally use sensing lines in a supply that you used an op-amp for, so you don't need regulators to make a regulated supply. All you really need is an op-amp and some way to set up a reference voltage and a sensing line to come back to tell you whether you're above or below the reference voltage. And that's how a basic regulator would work when you're just using a single op-amp. And the examples of that are like the early CS series, which I think are done really well. There isn't really a need to use a sensing line, because you can just do it this way by having a resistor come back to the chip within the same circuit board. I can't see a reason why you would need to take this sensing line off the board unless you ran it straight to the voice cards, which is what Yamaha did. And that makes sense, because if you're using a lot of power there, you would want to make sure the voltage was right. But in this case, Moog don't do anything that elaborate. What they do is just have the sensing line. This is for the this is actually for the -15 ground. Hang on a second. I'm going to getting ahead of myself. -15 volt. Okay, here we go. This one here, this middle supply, +15 volts. You can see the sensing line for the +15 still goes off the board and through the connector, and then it just ends up stopping right at the other end of this wire on the power distribution board, where it gets connected back to the +15 volts. So the sensing line only goes as far as the very next circuit board before the power has been distributed to any other boards in the synth. So if we have a look up here, yeah, so this is the DMUX and the power distribution board. You can see all the connectors for the power, where it gets distributed. This is the main set of connectors that comes from our power supply. And you can see pin, where are we? We're at the plus 15. Let's see which pin that is. Sensing line is on 10. Our voltage comes out of 9. Let's have a look. 10 here, plus 15. Look at our sense line, 9. They get joined together. And that literally happens on the bottom of that connector. So the sensing line only goes as far as the end of the cable, which is just pointless. They should have just shorted it out at this end of the circuit board. The result is that if you have any connection issues between those plugs and the sense line doesn't come back properly, you're relying on this resistor anyway to feed back your voltage, so the sense line's pointless. And that can cause big problems where there is no way for it to get back on this board. And that happens down here in the 5-volt supply, where there's a sensing on the ground. And if you have connection problems here, which is what I had in this synth, if these two get disconnected, all kinds of things go wrong. So why you would have that go through a plug and then just back again is beyond me. So we can double check this too. So this is, okay, so we're on the common for the 5 volts, plus 5 volt supply. Pin 3, sense pin 4 is the ground. Here we go, pin 3, pin 4, and you have a look, they're joined at the bottom of that connector. So they don't go anywhere. Now it's interesting, why would we have a sense line on the ground? Well, I've thought about this a little bit and I can't think of a reason, not at least in a synthesizer anyway. I mean, I repair scientific equipment and some of them have sections of the circuit board that are floating at significantly higher voltages than other parts of the circuit board. And the reason is that sometimes if you've got a very high voltage part of the instrument and you want to do some processing on that high voltage signal before it's stepped down, so to provide some analysis or some buffering or something, you can actually put ICs in that really high voltage part of the circuit. Say you've got a part of the circuit's at 5,000 volts, you can put ICs at 5,000 volts as long as the ground is 5,000 volts minus 5. Because essentially in electronics the ground is defined as what you want it to be. As long as there's only 5 volts across an IC, it'll be powered as normal with 5 volts. It doesn't matter if one end is 5,000 and the other one's 5,005. The chip itself will only see 5 volts. So there are applications where ground is raised, but then again, I don't know why you would use a sensing line on that. I can't think of an application where it would be needed. So to have it in a synth, I can't explain it, and it just causes problems, particularly on the 5 volts where there's no internal bypass on this power supply board. So when this is unplugged, they get disconnected, and that causes issues. So let's have a look at the 5 volt supply and explain what the problems are. So firstly, these ICs, they're normally powered from, the data sheet says anywhere the minimum of 9.5 volts up to 40 volts. And what's coming out of here is on the lower limit at 11 or so, maybe 12. They could have powered this chip of this supply, but it would have been unregulated. But they've chosen to do it from the positive 15 side. So if you have a look at this is our bridge rectifier for the positive 15. I think it's about 24 volts or so that comes out of here from memory. I haven't measured it for ages, but you get this voltage coming out of here, and it's stepped across this Zener diode, which is a 12 volt Zener diode. So these ICs are being powered from 12 volts. And that may have been the reason they've just chosen 12 volts across all 3 ICs. Is this the same Zener diode? between the positive and the negative of the IC. So these ICs are getting 12 volts, 12 volts. And if you've got a supply that's 11 or 12, it's not high enough. So that may have been the reason why they've taken it from up here, just to keep the same, a higher voltage going through the Zener, so it's more stable. So we've got the higher than 12 volts coming across this Zener diode. This chip turns on with 12 volts. It will have a look at the sense line, or what voltage is coming back from the 5. Now initially, when you first turn it on, there'll be nothing in this line, it'll be ground, so this will come back as quite low. So the IC will turn these transistors on to let 5 volts through until the feedback we get equals 5, and then it's happy. Now the problem is that if this chip is on, it doesn't necessarily mean that we can supply 5 volts, because if you have a look at this, so this is our positive for the supply, it comes through here, through our diode. It needs to return to here, to ground, because a full complete circuit will be going out here and then back again. So we have to make it back to this ground. So we're going through here, we power the chip, we come out here. If this isn't connected, it won't come back through this line, 15 volt common, and return to where it came from. So we won't have completed the circuit. So it's really important that when we unplug this big plug, that we connect this ground from the 5 volts to the ground to the 15 volts, or this chip won't turn on. It's also equally important that we have this 5 volts somehow going through a load and coming back again, which would happen through this resistor here. So that's okay. So we've got voltage that's able to come through this transistor, fill up this line, give us some feedback. This guy can turn it on and regulate. So the 5 volts should be pretty stable, even if these two aren't connected. But the problem is when we disconnect them, we disconnect all of them, we break the loop between this sense line on the 5 and the minus 15. And so this chip doesn't turn on. So when we unplug this big connector, that's the reason why we saw 0 on the 5 volts, even though this 5 volt circuit's potentially on. The IC that controlled that voltage had turned off. So when we unplug this supply, the first thing we need to do is turn this chip back on. So the way to do that is just to connect the common between the 5 volts and the 15 volts. Then that powers up this chip, and we will get 5 volts coming out here that we can measure. The other thing that goes wrong when we unplug this supply is we actually decouple the positive 15 and the negative 15. Why is this an issue? Well, it's not an issue that they're decoupled. We could still take these as two positive supplies, which is what they are, and we could measure 15 volts between the output and ground. And in this case, if this supply is decoupled from this one, it also acts as just purely positive supply, because you can see that the transistors are the same way. It's using the same IC. This is 15 volts and ground, just like this one is 15 volts and ground. So we've got two positive 15 volt supplies here that we could measure. The problem is, though, is that when you disconnect that plug, the sense line on the ground comes back through a diode. Unfortunately, the power for the chip and the ground isn't exactly the same, and I think that's what causes that voltage to be a little bit different, because normally what would happen is you would have your 15 volts coming through this resistor divider, and that would be referenced to ground because these two are joined on the next board. So if we look at pin 7 and pin 8, up here, pin 7 and 8, if you have a look, right at the bottom of the connector, they're joined. So when this is plugged in, 7 and 8 are shorted. Let's have a look at 7 and 8 here. Yep. So here is ground. Now the problem is when they're unplugged, here is no longer ground. Actually, here is ground. So we've got a diode in the way. So our reference is thrown out. and that diode just stuffs up our feedback on our sense line. So this will no longer be 15 volts, and that'll be the reason why when we unplugged, we got 16.5 between here and here. Now, let's explain how two positive 15 volt supplies equal a positive and negative dual rail supply. Well, this is what I explained before about having the two 9 volt batteries connected together. If we just connect the positive and the negative of these two and call that ground, then we've got, the reference 15 volts below and 15 volts higher. Now these are drawn the wrong way around. I would have drawn this supply lower, because if you have a look up here, it's this plus 15 volts goes to common, and here the ground from the plus 15 going to common. If we call this 0, this is minus 15 relative to that. You could look at that and say that it's lazy, but it's good in a way because it reuses components, so it is a little bit cheaper. And it regulates just fine. Yeah, but it's just interesting to note that these two, they're not designed as a positive and negative matching supply. They're both positive. It's just the way you connect them. That's just about it for this supply. The only other thing is this 5 volt raw line, which is taken from before the regulators. As I said, that goes to the 6 volt regulators on the panel board. And there's another line that I wanted to show you. This line goes to our RAM. So this is our memory protection early shut-off. So you can see that this goes to a point that is before any capacitors. So once this, in fact it looks like it may even be half rectified. So this this voltage line will shut off earlier than all the others. When we flick the switch, this line will shut off first, and then the 5 volts will be slowly dying through this capacitor. The 15 volts will slowly die through this capacitor. Minus 15 will slowly die through this capacitor. So this line has shut off way faster than all the others. So this allows us to turn off the RAM before the synth starts shutting down generally, because we don't want all the ICs to put random data on those write lines to the RAM and override our memory. So with this line shutting off first, we can safely shut off our RAM, and then as all the other capacitors die, all the other circuits can switch off and do whatever they like, and our RAM is safe. So let me try and find that circuit. Power shutdown. When you have a look here, we follow this line out here, SEC. So that's it. Once the power from this line shuts off, this op amp will shut off all of these RAM chips, and the battery backup will keep them, keep the memory stored, but they'll no longer, the write lines, the chip select lines will no longer be enabled. So they're essentially all, they're saved. So that's it, I think, for this supply and the schematic. I did mention that about the heat. Yeah, this supply does get hot. Now, normally when you talk about heat, you talk about the number of watts something is dissipating, and that is related to the voltage times the current. Now, the thing about linear regulators is that the current stays the same through the regulator. So if we want to design this to still power our circuits but dissipate less heat, we can't change the current, because the current is what these circuits under load, what they demand. So the only way to change our heat dissipation is to change the voltage that's dropped across these transistors The main ones are connected to the heatsink. So if we keep this side, our voltage that comes through the rectifiers, as low as possible, we can keep our heat dissipation as low as possible. Now, the voltage that comes out of here is a lot higher than what I would like. I think we get about 24 volts AC. I'd have to measure that again. But once that's rectified, that's high. It's 1.414 times higher because it's a full bridge rectifier. So we're talking significantly higher than 15 volts. And the reality is we could have gone a little bit lower. Particularly with the modern linear regulators, they don't need a voltage that's that much higher. Maybe this is a factor of using 723s. We needed a bit more voltage drop just because of delays and things, but it's way higher than it needs to be. So if these transformers were replaced with something that emitted something a little bit lower, then our heat dissipation would be greatly reduced and we wouldn't even have to replace the power supply board. Yeah, I've redesigned this supply again as a linear analog supply, and I've used modern regulators and as a provision for having a lot lower voltage come in and less heat dissipation, which is ideal for the Memorymoog, but I haven't used the supply. I got some boards made up and just tested it and that was it. But I'm still sticking with the original. There's one thing I like about these original supplies is that if you look at synths that were really great, that are really revered, that sound wonderful, there's always something quirky about them. When you go and have a look at the schematics or the way they're designed, there's always something a little odd that we wouldn't do today. And I think that's part of what makes them special and different. So I'm loath to change anything here because it forms part of what makes the synth special. And I have, with other synthesizers, sterilized them by accident by doing things like replacing the power supplies with better ones and doing filter mods and all that kind of stuff. So I've chosen to leave this one how it is. I mean, essentially works fine. You just have to have it plugged in. And if you don't, you need to join some pins. So let's now move on and I'll show you how to unplug this supply and still measure the correct voltages. So a few things we have to do. We have to join the sensing lines to their main voltages, which is not necessarily required on the positive side. So you see they're joined by a resistor. Here the 15 and the sense lines joined by a resistor. So we can leave these ones out if we want. But we must join all these grounds. So at least here the minus 15 and the sensing line and the plus 15 ground and the sensing line. And definitely this 5 volt and its sensing line. Once we join these two with these sets, the supplies work individually. But again, this chip won't turn on until we complete this circuit that's powering it up here to here. So after I join 3 and 4 and 7 and 8, I also then put a jumper between one of these two and one of these two, just to complete the circuit and turn the 5 volts on. And once you've done that, you can measure and calibrate perfect. And when you plug it in, that voltage will remain. So that's how I prefer to do it. I don't like calibrating supplies while they're still in the synth, just in case anything goes wrong. Or especially the first time you power them up, you want to check that they're okay. So I do unplug and I just put the jumpers on. And it seems fine after that. Okay, let's jump back on the synth and I will actually do that and show you. Okay, so the one thing you are going to need is lots of these. I think they're called parrot clips. These are the small size that you use for ICs. So I've got two sizes. The larger ones I've run out of, because there's a fair few that you do need. If I go through what I've done, pins 1 and 2, 5 volt sensing, join them two together. If you don't, then that resistor between the two is in the voltage dividing feedback of the regulator, and that extra resistance will bump the 5 volts up. Then pins 3 and 4 are the ground and the ground sense for the 5. Now you must join them because they get broken when you pull the plug. Then the next set of ground pins are for the 15 volts, because remember you need to complete the circuit of the 15 volts through the regulator that powers the 5 volts, and that's done through the grounds. So on the 15 volts, pins 7 and 8 are ground, so you need to join those and then link those two, 7 and 8, back to 3 and 4, so that the grounds between the 15 volts and the 5 volts are linked. So you can see I've used black clips for the grounds and red for the voltages so I don't get them confused. Now the 15 volts has the same problem as the 5. When you unplug it, there's an extra resistor that gets added to that voltage divider. Yeah, so it's a good idea to short that as well. But the main thing was that diode in between the sense line and the ground that puts this one off. Short the grounds out, join them together between the 15 and the 5. Then you're okay. Now, so in this case, I'm measuring the 5 volts with my red probe and the 15 volts with the blue probe. Okay, so we've got 5.02 for the 5 volts and we've got 15 volts, 15.09 for the 15 volt rail, and you can see there's no noise in either one. It's on 2 volts per division here. I don't think you can see the divisions on the video, but that's the height difference between 2, 5 and 15. Now you can calibrate and get it right because we have corrected all the problems that happen when we unplug that plug. So now I have that, my screwdriver on the 15 volt, and I can change that to exactly 15 volts if I want to. And the same with the 5, which is over here. Not sure whether you can see that. It's in the shadow of my hand, so that 5, oh, it's a bit touchy. Yep. So now, when you plug that back in, those voltages will be correct. It's a lot of effort to do, but I highly recommend it. I like calibrating power supplies before plugging them into the synth, just in case they're a little bit out, as often happens with very old synthesizers. So that's it for this video. It's been a long one. Oh, there's actually a couple of things I want to mention. When you've got the Memorymoog this far apart, which not many people do, make sure you go and replace the chip beds with some machined pins. Now these two groups of 3, they carry the voltages to the voice card, because not only is this board the power supply distribution board, it's also the sample and hold circuits for the control voltages. You can see all the capacitors. So the control voltages go out via these chip beds. So I always replace the one that's used for the ribbon cable. Now all these 3 are the same. I think it was because there's 3 pairs of voice cards, but in this Memorymoog they ended up just using 1 ribbon cable per set. So I've only replaced the 1. And other things, there are capacitors on this board. There are small ones here normally. So there's 3 on the left for the, let's see if we can do it by memory, 5, 15, minus 15, something like that. There's another one over here for the 10 volts, which is generated on the board. These capacitors are only 10 microfarad, and they are filter caps or power storage caps for those voltages. So they don't have any purpose besides buffering those voltages before it's sent to all the other boards in the synth. So I like to uprate these ones. They are an extension of the capacitors, the smaller ones on the board that buffer the voltages after they're regulated. So I like to uprate those ones. I don't do it anywhere else in the synth, but for here, it's nice to have buffering on this board because this is the board that distributes the voltages to everywhere else. So that's it for the tips even. So we're finally done. I hope you enjoyed it. I may do some more videos. I have one where I clean the switches on the front. These switches are completely different to what you've seen before. They are nuts. And I have done a video cleaning them. But until then, thanks for watching.